Live stream a little better. Welcome back to machine design. Today we'll be designing machines. So what I wanted to start out today's lecture with was we need to talk about the project. Over the course of this week, I am going to be uploading a bunch of documents to the Canvas to detail a little bit more about what exactly I'm asking from you about the project. But ultimately, what I'm going to be giving you and what the purpose of doing this project is you're going to have to completely design, analyze, and construct a robotic leg this semester. Now, if COVID causes our campus to close and we don't get to finish out this semester, so be it. There's nothing I can do about that, but I will be doing everything that I can to try to make sure that we get this building project off, because it's one thing to design something like this. It's a completely secondary thing to be able to physically implement something like this. So just the requirements of the project are you're going to be given some kind of rotational axis input into your system. Okay. Yes, you will have to design that shaft. That rotational axis will have to go to some kind of 4-bar linkage or something that powers the movement of your leg. That will drive vertical up-down motion. Oh my, this marker is already starting. This is a brand new marker too. Don't fail me yet. I believe in you. Huh, okay, it's working. But it will power some kind of motion that basically will generate a robotic leg movement. Now, one of the things that you're going to have to be able to do is, as this rotates around, it is going to have to lift the leg up 7 inches. The total distance from the point of actuation to the bottom of the leg is 20 inches. And, come on, new marker, stick with me, is 20 inches. That's full extension. At full retraction, it'll be at 13 inches. And you will have to include in your joint right here some kind of a spring such that when the foot hits the ground, it's not transmitting all of the forces all the way through. The importance of doing something like that, having a spring, is it gives it a little bit more control. It reduces the shock. For those of you who have already taken 350, it's important to take the inputs into the system and mitigate them so that you don't experience the full weight of that contact force. Your leg, as it is right now, is constructed such that it is able to handle those forces, but it actually has areas of compression in the cartilage here in your knee, in the way your hips move and rotate, and even in your ankle joint. Those cartilage joints will absorb a lot of that impact energy and reduce the total amount of force that is transmitted to your upper body whenever you take a step or whenever you hit the ground with your foot. So you're going to simulate that by having a spring located at some point in your design. Now, your design doesn't have to look anything like this. This is probably the simplest design possible. But how you design the connection points for this robotic leg are ultimately going to define how that robotic leg moves. We will talk about this at a later date. We will have an entire lecture on 4-bar linkages at one point. Unfortunately, I didn't schedule that till later on in the semester, and I am coming to realize that that probably would have been a better lecture for next week. So I am going to be adjusting the way that our course is being taught, just in general, because we need to cover that material right away. What we'll be talking about today is going to be just a continuation of how you analyze stresses. We talked about this in the in-class session last week, but we're going to be continuing to talk about how to analyze stresses, how to determine stresses, measuring stresses, those kinds of things. So that's the point of today's lecture. So we talked about normal stresses and shear stresses in our in-class session. Here, oh, come on, new marker. Come on. Come on. Oh. You know what? I'm going to believe that this marker will eventually come to its right mind. But I'm going to grab another one. Just work. All right, so what we have with normal stresses is okay, making sure I'm spelling this right. Doesn't look right the way I wrote it. Normal stresses occur anytime the load is the two loads are axial to each other. They fall on the same axis. Okay. Okay, let's say we have a very simple bar like this, and it's a hollow tube. Let's say this has inner diameter is 3/4 of an inch, outer diameter is 1 inch. Okay, so it's got a 1/8 inch wall thickness on there. All right, and let's say we take this and we apply a uniform distributed load to the end of this tube, and we're going to pull it in tension, or we could put it in compression or something. Okay, a tensile force T, let's say that's equal to 3,000 pounds. Okay, so this is the force that's pulling on this pipe. Now, the important thing to note, and the thing that you've got to remember first and foremost, is this. Stresses do not depend on the material. Okay? It doesn't matter if this is plastic, wood, metal, anything right now. Whatever the stress is on this material, it does not depend on the material. Stresses are a function of load and geometry. Okay? So if I'm going to go sigma, sigma is a function of the forces and the geometry, which I'm going to go ahead and write geometry as geometry. Yeah, because, okay? This is what the stresses are. There is only a consideration for forces, and there's only a consideration for geometry. Okay? Whether or not failure occurs, that then becomes it becomes indicative of the material type. It becomes indicative of stress concentrations, all of these other types of things, material choices, fatigue, multiple things. Okay? We will get to failure later on in the semester. But for right now, what you need to know is, if I give you this, and I say, this is made out of carbon steel, and I give you the exact same problem, and it's made out of aluminum, those components will face the exact same stresses, because stress does not depend on the material. It only depends on the forces and the geometry. So, with that said, what is going to be the stress in this component? And can we draw a stress distribution of what the X, Y, and Z directional stresses are, shear stresses, everything? Can we do that? Well, yes. For this problem, it's actually fairly easy. So we'll go ahead and say that this is in the X direction, Y direction is vertically, Z direction will be coming out like that. Okay, so this is the free body diagram because it's very simple. Now I'm going to go ahead and take this metal bar right away. I'm going to apply 3,000 pounds. Now the formula for normal stress is sigma is equal to F over A. Okay, sigma in the direction of F. So that means if this is sigma x equals Fx over A, and that is A perpendicular to the X plane. Okay, so that is, you're gonna, if we cut this, if we created a plane based on the X, you would only be able to see Y and Z. Okay? So that is what AX is. Similarly, sigma Y is equal to Fy over AY. What that means is the normal stress in the Y direction is equal to the force in the Y direction divided by the area that is generated from the X and Z axes when making a cross section. Okay? And then similar, sigma Z is equal to Fz over Az. You could also write AX, some people do this, as AYZ. Because that's what it is. It's an area that is generated in the YZ plane, which is also happens to be, another name for that is the X plane. Why is the X plane? Because X is perpendicular to the plane. You can define a plane by a line that's perpendicular to it, a vector that's perpendicular to it. So, just different terminology. Anyways, so what we have here is, I'm going to go ahead and erase this now. Doing our free body diagram, we only have one force in any of these directions. Okay? Sum of the forces in the Y direction equals 0, because there's none. Sum of the forces in the Z direction equals 0, because there's none. Sum of the moments in the XX direction, sum of the moments in the YY direction, sum of the moments in the ZZ direction, all equal 0, because this here this has no moments in it. This is just straight tension, straight compression. Axial loading does not produce a moment. So that's nice. We only have one, and it's sum of the forces in the X direction equals T minus T equals 0. Because you have T on both sides. And you're having T? Oh, jolly good! It's on both sides. Oh, that's what all those Brits wanted from us in America. Tea on both sides. We drink Kool-Aid, which was invented in Hastings, which every Nebraskan will tell you at one point in their lives. Anyways. Now I got sidetracked. Also, I'm thirsty. Dang it. Right. So, this is my formula. I know what my X force is. It's this right here. Okay, if I were to take a cross section, it was cut it right there, which is on the X plane or the YZ plane. What you'll see is you got this tube, and then you got a force coming out of it, and at that same location you got a force going into it. So if I draw them on top of each other, it makes absolutely no sense. But that's what the cross section is. So instead of doing that, I'm going to draw more of a three-dimensional interpretation of, here's a tube, doop, doop, and it's just a really small piece, and I have a bunch of forces here, all of them in this direction, and I got a bunch of forces here, and all of them in this direction, and it's just pulling it in tension. Okay, and all of those forces are going to sum up together to force T. And we're going to assume that that force T is evenly distributed around the tube. So what you have here is sigma is equal to F over A, and this is sigma in the x direction, F in the x direction, and the area in the x direction, which happens to be a YZ on the YZ plane. Okay, we don't know what this is. We do know what this is. We can figure out what that is. Okay, F in the x direction is T, which is equal to 3,000 pounds. The area in the x direction, you have an open tube here. Now, this is where I'm going to introduce a fun tool that I really like using. It's called the back of the book. The tables in the back of the book, there's tons of tables in here. It has everything from shear and I'm gonna try to get this so the light captures it so you can actually see it. If shear and bending moment diagrams, they tell you exactly how to figure out what the formulas for the shear and the bending are. Just really useful tools here in the back of the table. These are people who have done the math for you already. So you can sit there and try to do the math yourself and prove these to yourself, or you can just use them, which is what I told you to do in mechanics and materials class. We're going to do that again in this class. Save yourself some effort. Don't have to derive these equations. Now, understanding how to derive these equations shows that you have some mastery over the material. So if you really want to try to derive these equations and prove to yourself that you're really good at doing statics, go for it. But I don't want to. Okay, table 18, A18, which here is on page 1044. This has a hollow tube down here at the bottom. This hollow circle, I can figure out the area formula. It's right there. So if I was dealing with a more complex shape, such as a triangle or a quarter circle or something, you can use the back of the book, or you can use the Google, which is also useful, to find some of these properties. These properties are generally available. This is a geometric property. Geometry and forces are the only things we need to understand the stresses here. So you've already got the geometry now. It's been calculated for you. It's in the back of the book for me. All I have to do is plug in math. So formula for area is pi over 4 times big D squared minus little d squared. Yo, little d! Yo, big D. Anyways, we've got all of these components now. I gave them to you in the problem. So we can just plug them in. So this is equal to 3,000 divided by pi over 4 times 1 squared minus 0.75 squared. Okay, now if I plug that into my calculator, which I brought because I'm fantastic and amazing, 3,000 divided by pi divided by 4 times 1 minus 0.75 squared, doop doop. And the stress, the axial stress that is generated by this force is equal to 8730.8. Now what are we using for units on this? Okay, what do we have on top? Well, this is something I gave you in pounds. So this is pounds divided by here, this is a unit of area, and the units that we used for both of our D sizes were in inches. Okay, but we squared both of them, so it ends up being a pound per inch squared, PSI. A pound per square inch, PSI. We usually use PSI, or will we use pascals in this class. Pascals are a Newton per meter squared. Okay, so this is what we're dealing with. This is what we have. This is the correct answer for the stress distribution along the length of the shaft. I don't understand your question, Orlando. So I'm going to ignore it. So when we're looking at this, how does the stress carry across the entire component? If we were to graph this component, starting from this side to this side, just along this component, how does that sigma x value differ? Well, we're assuming that T was evenly distributed around both ends. If it wasn't, there is going to be a difference at the very ends in sigma x. Because at the very ends, what we see is that there's just a stress variation. But if we're going to assume that the force was nicely distributed around the entirety of the hollow tube, then what we will see is we will see a constant sigma x force that is created from that normal stress, okay? The geometry of this component do not change. If they did, then you would actually see it vary. Like if it was thinner on this end and thicker on this end, the geometry is changing, the force is staying the same, so what you have is on this end it'd be really small, on this end it'd be really big. The stresses would be bigger on this end than they would be on this end. You'd have something that looks like that if the geometry was different, okay? But we have a uniform geometry, so this is what our stress looks like. This is what we get for our stress, and it's constant. The sigma y and the sigma z stresses, well, we have no forces in those directions. Because we have no forces, you go in to calculate sigma y and sigma z, your fy and fz are 0. You have 0 stresses in those directions. That is true. You actually do end up having a deformation in those directions. You do not have stresses. The front of the book is nice too. Is there really a table in the front of the book? I don't have a table in front of my book. Huh. But anyways, whatever. So this is axial stresses. Axial stresses, fairly straightforward. The calculation is just this formula over and over again. No moments, no having to worry about moments there. But when we talk about shear stresses get a little bit more funky. Okay? So when it comes to shear stresses, shear only occurs in off-axis loading. Now I will provide a note here. You will not have shear stresses, you will not have shear loading that occur in the absence of a moment. Okay? An example that I like to provide is, let's say you've got a beam that looks like this. Okay? You know what? What the heck? Why not use the same exact cross section? Okay? It's a circular cross section with inner diameter is equal to 0.75 inches, outer diameter is equal to 1 inch. Okay? Just another hollow tube. Using the same area cross section, whatever. When we load this, what we're doing is we can actually generate a shear and a bending moment diagram from this. Now, we're not going to focus on bending moments until the next video, which I'm about to show you. So for right now, we're just going to focus on the shear forces and the shear force diagram. Okay? Shear force is written as V. What you have here is, according to the book, the convention for a positive shear force, let me grab this real quick, but that convention is that, I just want to make sure I'm teaching this to you right. Shear is positive when you have a situation like this. This is called positive shear, where on this side it's being forced upward, on this side it's being forced downward. Okay, so if we have on the left side we have positive shear force, and on the right side we have a negative shear force, then we have a positive shear situation, positive shear force overall. Okay, so if I were to break this component right here, what I would have is I have my shear force on the left, and what's being carried across the cross section is a downward shear force. Now, according to our convention, with this being positive and the opposite being negative, this is a positive shear. So let's go ahead and call this F1, F2, F3. We'll go ahead and say maybe this is 36 inches long. F1 is going to be equal to 2,000 pounds. F2 is going to be equal to 3,600 pounds. And F3 is going to be equal to, I don't know, 1,600 pounds. Okay, so that's what we're dealing with. And then this would be, I don't know, some distance. I don't want to do the calculations in my head. In any case, saying we've got these three forces and saying based on geometry that's how it works out, whatever. What you've got here for your shear force is your shear force starts out on this side, you've got 2,000 pounds, which means that across this cross section, in order for this not to accelerate upwards, this shear force also has to be 2,000 pounds downward. Okay, and that's true if we break it here, 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 anywhere from here to here. That shear force is identical. It doesn't matter what the width of this is. As long as we are between F1 and F2, the shear force that's being exerted is going to only be 2,000 pounds. Has to be. And the moment's going to change so this doesn't rotate, but the shear force itself is going to stay constant. So what we have here for our shear force diagram is it's going to be a constant positive 2,000 pounds. Okay, now we'll go on the other side and we'll break it from here and go this way, this way, this way. Okay, going backwards. Now what we have here on this side is we have a force upward 1,600 pounds, and we have a force downward which is going to also be equal to 1,600 pounds. Okay, and that's going to be true whether we cut it here, 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 all the way between F3 and F2. That shear force is going to stay the same. Now the moment is going to change, again, as I've said, but the shear force stays constant throughout that. So what we have between F3 and F2 is we have a negative, because you'll notice in order for this to be positive, the shear force on the left has to be up and the one on the right has to be down. Well, we have that exactly backwards. This is a negative 1,600 pounds. Okay, where that's 1,600 negative. Okay, and right at F2, it jumps between here and here. That jump has a total length of 3,600 pounds. Okay, this jump from here to here has a length of 2,000 pounds. This jump from here to here has a length of 1,600 pounds. Okay, so on our shear force diagram, every place we have a jump, it signifies an increase in an application of load. Okay, so this is what our shear force diagram looks like, and let's say I'm going in the XY plane. Okay, so this would be shear force in the Y direction, because that is a Y-facing force that is acting on the YZ plane or the X plane. So now we know what the force is. In general, tau, which is our shear force, average is equal to the shear force in the Y direction divided by the area in the X plane, which also happens to be the area on the YZ plane. Okay. We also know from our analysis last class, and what we know from mechanics of materials, is that this shear stress, which is the average in the Y direction on that X plane, is going to be equal to the X directional stress that's located on the Y plane. So they're both the same thing. So the shear stresses that are located here in this direction are going to be the same as the shear stresses located here in this direction. That's just the nature of the beast. Okay. So if we were to calculate the average shear stress, I mean, that's nice. It gives us the shear stress over the entire area. But the full extent of the shear force is not carried and distributed nicely around the entire cross section. The shear stress ends up being I'm trying to find the formula for it. It's kind of a weird formula. The actual distribution tau is going to be equal to VQ over IB, where here tau is YX or XY. You can write it either way because it's the same stress. That is the Y directional stress that occurs on the X facing plane, or the X directional stress that occurs on the Y facing plane. Same thing. Okay, so this is equal to V in the Y direction, or if you have a shear force in the X direction, times Q. Q is in the, again, it's the cross section on the X facing plane. IXXB is a measurement in the Y direction from the centroid. So yes, this formula is kind of ugly because it involves a Q and an I and a B. What we end up doing, and what I suggested doing for this class, is instead of using this type of a formula for shear, just go with your maximum shear stress. There are concentrations given in table 3.2 that shows just generally some different ways of calculating a maximum shear stress. 3/2 is about equal for, well, it's true for a rectangular beam. 2 ends up being the thing for a hollow, thin-walled, round tube. So it ends up being 2 V over A for a round tube. Okay, and the location of that maximum shear stress is going to be at the center, right here and here, of that hollow tube, facing upward. Now I'm just going to go ahead and say once again, assume that it's at the maximum shear stress. Shear stresses, you can use this formula if you really, really want to. It's not going to hurt me any. But assuming that it's at the maximum shear stress, we'll give you a more conservative estimate. And I like conservative estimates. It means things are designed so that they don't fail. But if you really want to use that formula, be my guest. So what we have is 2V over A. So if we know what the shear force is at every location, then we know what the area is at every location. Our area is that A is equal to pi over 4 big D squared minus little d squared. Yo, big D. So with this area formula and with our shear diagram that we have now, we can figure out what the shear stresses are at this location and at this location, going along the center line of this. I'm just going to only calculate the maximum. Here, shear force is 2,000, positive. Here, shear force is negative 1,600. So for this region right here, our tau max is equal to 2 times 2,000 divided by pi over 4 times 1 squared minus 0.75 squared. Okay, so over here, our tau maximum, let me plug it into my calculator. 2 times 2000 divided by pi divided by 4 times 1 minus 0.75 squared is going to be equal to 11,641 psi. Because again, we're dealing with pounds and square inches. Okay, on this side over here, our tau max is equal to 2 times negative 1600 divided by our pi over 4 times 1 squared minus 0.75 squared. Okay, so doing that again, we get a tau max on this side of 9313 psi. Okay. So we could then draw this as a diagram. The shape of your tau, the shape of your shear stress, if you were to plot the shear stresses, maximum shear stresses along this cross section, the shape of that graph would be identical to this. So it would look like this. If you're graphing tau max, it's here, goes down, goes here, goes back up. Where here this value is 11,641, and here this value is 9313. We have an identical cross section across this entire thing, which means that since the stress only matters whether it's about its force and its geometry, since we have an identical geometry across this section, then all we have to do is take the forces and multiply it by some factor to get the stresses, which is why you have this. You're going to have the same thing for the normal stresses when you have that situation. Okay? If the geometry changes, you will have a different graph. It will vary. If it tapers out, goes thick, well, maybe this starts thin, gets really thick, goes thin again. Okay? What you'll have is it'll start here, and when it gets thick, your tau max will drop, and then it'll increase again at the ends, because that's the way it works. Alright, I'm going to go ahead and stop this video. Oh, right, thank you. This is negative. Thank you for pointing that out. Okay, I'm going to start the new lecture. It's going to be lecture 6. Lecture 6 is going to be over bending stresses and torsional stresses. So we're going to jump into that right now. Okay, so I will quit out of this lecture.